Okay. Yeah, that should be it. Okay, today's goal is to for you to understand what is, as I already said, what a signal is, what an FFT does, what a power spectrum density is, so we can build up on that for next week. So let's try jump right in. When acquiring those electrophysiological signals like EEG, MEG, EMG, or even a cardiac, you basically end up with something that looks like the image you're seeing right now. You have this multitude of channels, a few less if you do EMG or cardiac, which is lucky in that regard, but it's going to be hard to interpret that. And you're going to have a patient usually standing right next to you, asking you, in this case, that's the EEG. What's my EEG saying and what can you see in there? And directly seeing stuff in there is rather difficult, which is why we do all that signal processing stuff. To basically give you an introduction, a frame of today's lecture, we have I have this overview here, which I kind of framed the data lifecycle. Initially, we have some neuronal activity, which is not going to be covered in this session since it's more on the technical side. And that neuronal activity is going to be picked up by a sensor, which then forwards the signal to an amplifier. Then we do some processing on the signal. Then we present the results, and we can basically tell the guy or the patient that we just acquired an EEG from what's actually up with this EEG and whether we can see something in there or not. So starting with the sensor, if you acquire those electrophysiological signals, you usually have either an analog or a digital sensor. And my guess is that most of you are going to work with an analog sensor. And the difference is basically that with your analog sensor, you have a continuous scale, like with a thermometer here, goes from 0 to 40, but there's no individual steps in between. It's basically, yeah, as the name says, it's continuous. Whereas with the digital sensor, that only can tick up on in the digits behind the comma here. There's no finer granularity in there. So let's take a closer look at the analog sensor that both most of us are working with. And as I already said, either those are reference-free or they are referenced. And if you work with a reference-free setup, like if you do MEG or if you do, let's say, even a questionnaire or something, you're kind of lucky because you don't have to consider yourself the thoughts on where to put a reference and whether that's a good place for the reference or not. So if you have a reference sensor like this windmill here, you're basically measuring a gradient. And that's basically, let's say, you have some wind that's pressuring onto the windmill from before the windmill. You have some wind that's pressuring onto the windmill from behind the windmill. And if the wind before the windmill is stronger than the other one, that wheel is going to turn around. And that's basically what you're measuring with your EEG or your MEG sensor. You're measuring current flowing from, let's say, from the side of the of the EEG electrode to the side wherever you put the reference, or maybe the other way around, something happening at the reference of flowing into the other direction. But a little more on that later. Yeah, as I already said, if you do MEG or have like a questionnaire, you're kind of lucky in that regard because you're measuring absolute measures. Like that magnetic field of MEG has this amplitude here, and that's about it. Whereas with EEG, EMG, and the cardiac, you have to select a reference against which you're measuring. So let's say you have your EEG setup here, or you have some EMG setup here. You can select one of those electrodes as a reference, for example, and the other ones can be selected as, yeah, basically, yeah, the locations you're actually interested in. And what you're measuring, as I already said, is the gradient between this blue one and the red, or this blue one and the red, or with the EMG, yeah, the difference between the blue and the red one. And to make that Zoom sessions that usually are super dry, a little more interactive and flashy, for lack of a better term, I thought it might be a good idea to integrate a couple of questions to basically keep you a little engaged and to make it, you know, more of a bi-directional discussion than me talking for 45 minutes about stuff I know or stuff I have worked on. So just, that should have worked theoretically. Now all of you should see the question that just popped up right on the slide. So let's go with it. I'm just gonna wait like 45 seconds so everybody who wanted to has had a chance to participate. So basically, yeah, 33% of you said that the activity from the reference is going to be visible in every channel, and 2/3 of you said no. And the answer is basically that you should never trust that Ask the Audience joke on the Who Wants to Be a Millionaire show, because you see it in every channel. Whatever happens in your reference is going to be visible in every channel you're going to record, because you're measuring the gradient between a site of interest and that reference. So whatever happens at the reference gets pushed into whatever you're looking into. So if we take a look a little bit closer into that, into our EEG example, that's basically it means that in every of those sensors here, what we measured against this reference in the middle, we're actually measuring what's happening at the sensor partially, and we are measuring in all of them partially what's happening in the reference. Yeah. Yeah. Oh. So usually you get something like that. You have the activity at the channel and you have the activity at the reference. And what you can do to get basically kind of rid of that activity is either you place the reference at some place there's no activity at all, which basically means that this red bar here will turn down to 0 and you will only get the blue activity, which is what you wanted. If you, let's say, have an EEG set up and you're trying to find a place where you're not going to have any electrical field, you're basically out of luck, because you're not going to find one, regardless of where you put it. So you're always going to have some residual more or less there. And if you're unlucky, basically you have say you have a setup that says the reference has to be at a specific point. It may be at an area where there's actually activity, which will basically then confound all those other channels. So what you can do is, for example, you can apply common average re-referencing, which is basically how to get rid of this red compartment in all those channels. That basically assumes that the red part is equal in all those blue components, whereas, of course, each channel has its individual contribution. And if we have a setup of, let's say, 128 channels or something like that, or 64 channels, and we have always the same component of the reference, if we average across those channels, we're going to basically have a super large component of the reference and tiny components from each of those channels. So if we subtract that average, we're kind of introducing a tiny bias by basically adding a little bit of the other channel of every other channel to the channel we are just looking into, but we're getting rid of this huge impact of whatever recorded at our reference. So, and that was kind of an idea from Luca, the PI of my lab, to provide you with some coding for those functions to basically help with the applicability of what I'm telling you right now. And this is a re-referencing function of a framework I wrote, which I can send a link to around later on. And what you basically do is you just put your data in there, and then it gets rid of whatever activity happened at your reference. And getting rid of that activity is crucial, because let's say let's say you have an unfortunate setup and you were investigating whatever happens at the motor area, of the cortex, and you put your reference right at CZ. So whenever somebody moves the arm or even something happens with that motor cortex, you're gonna pick it up at CZ because it's sufficiently close. And that, for example, would be like a prime application case where you would want to go apply common average re-referencing. Another would be if you had a strong artifact in your reference, and it's only in the reference. By applying common average re-referencing, you're removing the effect of the reference onto the signals, thereby removing the artifact. So having covered that first idea, the sensor, I suggest we move on to the second one, which is going to be the amplifier. And if we look at our data here, that had to be amplified and digitized and quantized somehow. So if we take a look at only one of those channels, we start with our beautiful continuous signal, which is continuous on the x-axis and on the y-axis. And that's basically something our amplifier doesn't like at all, because our amplifier is usually a digital machine, and digital machines deal in absolute increments, which means, let's say, it only knows increments of in steps of 1, 2, or whatever. So we have to get that from continuous to discrete on the x-axis and on the y-axis. And getting that to discrete on the x-axis is usually called sampling, which means taking a snapshot of your signal every n seconds. Usually you take like a couple of thousand snapshots per second, and each of those snapshots becomes a data point. And then, of course, you want to have a high sampling rate, taking a lot of snapshots to basically capture as much information from your signal as need be. But on the other hand, if you have a super high sampling rate, you're going to run into the issue that your amplifier is likely not going to support that, because they are limited in sampling rate, because it becomes really difficult if you go really high. And the other issue is you're going to create super large files that you neither can work nor store with in the end. So you should select the sampling frequency you can work with, and of course the amplifier supports at some point. And that's basically where the first kind of roadblock would hit us in form of the Nyquist-Chen theorem. That basically says that if you want to collect all information that's in a signal, and the bandwidth of that signal is limited to a certain frequency f, you have to sample at more than twice that frequency f. So that basically has two issues here. It assumes that our bandwidth is perfectly limited. And if you take a look at those electrophysiological signals, usually they have a low frequency component, and then they decay slowly, but they never ever reach zero. There's always some power. So you don't have a bandwidth limited signal at all. And the other issue is that you have to select a sampling frequency greater than 2 times the highest frequency you expect in your signal. Not equal, like it's at least 80% of the literature. It has to be greater than. Equal does not suffice. So let's take a look at that. What basically happens if we simply ignore the theorem and apply a lower sampling rate. Let's say we have our signal here, and we want to sample that. So we grab a couple of snapshots of the signal, and this is basically already too low sampling rate. And if we try to fit a sign through those individual data points here, this would be one option of fitting that sign through the data points here. And as you can see, it's not even close to what the white lines look like, but it would be a viable approach to do that like that. And by increasing those data points to a higher count, you're basically changing the possibility of me fitting a bad sign to your data. Because if you have a high enough number of data points, to be more precise, those more than 2 times the highest frequency in your signal, you're basically leaving me with only the option of fitting a sign to those data points that exactly fits to your data. I can't or the algorithm can't do it wrong anymore. That only works if you undersample your data. and we'll like dive way deeper into that a little later. And yeah, that's basically what's called aliasing in your signal. If you undersample your signal, you make it aliasing, but more on that later on. Another issue you may have in your signal is harmonics. Harmonics is, let's say you have an effect at 20 hertz and you want to sample that. And you record something that looks like this beauty here, which doesn't even closely resemble what you wanted to record in the first place. That may be because your signal that you recorded here came from a source that had a really high impedance, and there were specific conditions met in the setup which are quite difficult to get rid of. And that basically resulted in having an effect at 20 hertz, and then one at 40, and another at 60, and one at 80. Basically, you can, if you have that unlucky relationship between super high amplitude and high impedance, you can have multiple replications of the original wave you wanted to capture at integer multiples or integer fractions of the signal you were looking into. And that's quite common if you look into deep brain stimulation artifact, which usually happens at 130 hertz. You're quite likely to see those at 260, 260, 390, and so on. Or you're also likely to see the same effect with if you're basically recording even in the, somewhat in the vicinity of power outlet, you're going to have line noise, but not only at 60, you're going to have it at 120, at 180, 240, all over the signal, basically. And that's called a harmonic distortion. Those are more difficult to get rid of. And the other effect I quickly wanted to mention at this point is ringing and ripple effects. And I just wanted to basically briefly skim this topic. A ripple effect is if you apply some filtering, as we will later see, or some other digital signal processing method. And if you're not, basically, if you're looking purely at the frequency domain of your signal and not looking at all what happens of the time domain, it may be that, let's say you apply a super strong filter, your signal becomes like literally rippled. And that will create an artifact in your data that you will have difficulties to get rid of, if at all. So you're going to be careful about that. Then when I looked into the Nyquist-Shen theorem in preparation for this workshop, I found this beautiful, what is that, like a mini lecture on what the Nyquist-Shen theorem does not say. It was quite interesting in terms of the way it was displayed. The things that if we have a signal at 1 kilohertz that we need to detect, we have to sample at 2 kilohertz, and that's not stating that this is not what Nyquist-Shen theorem says, and it's actually not what it says at all. Pushing that a little more into like our realm of application. Let's say we want to detect 20 hertz signals, so we sample at 40 hertz, which is an awfully bad idea. You're going to have line noise, which is going to be around 60 hertz. So you're going to undersample your line noise. You're going to have the majority of your power in the undersampled part. So if you have say, let's a dBs artifact, and you have a line noise artifact, and you undersample both of them, or even one of them, you're going to introduce a severe bias to both your the undersampled signal. So when selecting that sampling rate, you have to not only consider like what is the signal I want to look at, but more along like what kind of frequencies could be in my signal that are of significant amplitude. Because if you skip them, you're going to alias them, and that's going to introduce a major bias into your analysis that you're like unable to get rid of later on. And important, the sampling frequency has to be more than 2 times the highest frequency in your signal. So if it's exactly the 2 times the highest frequency in your signal, that highest frequency is the frequency where you cannot reconstruct the amplitude of, which is kind of a limitation of the sampling. So you would use, let's say if we sample our 20 hertz signal at 40 hertz, we would get the amplitude till 19 hertz, and at 20 hertz we would lose it. we couldn't know what the amplitude at 20 Hertz was. So taking that back to our beautiful signal that we just sampled here. Yeah, it's time for the second quiz. Amplifiers. Launch. So what do you think is the highest frequency present in our sampled signal? The highest frequency in the source signal, every frequency equal to or lower than half the sampling rate, or the highest frequency in the resampled signal? I'm gonna wait like 45 seconds again, or a minute. It's a little more complicated. Okay, I'm gonna wait a couple more seconds since we've still got a couple of votes coming in. Okay, let's share the results. So we got a relatively equal distribution again, which is kind of interesting. The highest frequency in the source signal, if that's your, let's say, 60 Hertz line noise, and you sampled at 40 Hertz, you're gonna alias that. And that's not gonna be the highest frequency component in the sample signal. If you're gonna have the highest frequency in the resampled signal does not, well, it doesn't, that it's kind of oddly worded on my end, but there doesn't need to be a power spike there either. What we basically have in our sampled signal is every frequency equal to or lower than half the sampling rate. But if we have a frequency which was above the sampling rate, that basically gets wrapped around into those lower frequencies. And I'm gonna go into detail regarding that later on a little more, but that's basically, let's say, if you sampled at no, I'm going to go into detail that later regarding that later on. It's not rush. So having sampled our signal, we need to quantize our signal. And as our amplifier is digital in nature, it only, as I already explained, it only knows increments of certain steps. So we basically have to define what those increments are. And that's basically what you define if you define the resolution on the y-axis of your EEG, of your EMG or whatever. And that basically means if you define those increment steps super, if you define them super large, you're not going to see any activity changes in between those steps because they're going to get discarded. If you define them super low and say, I'm just going to go with a super large range, you're going to run into the issue that you only can represent a certain amount of numbers with your digital amplifier. Like if you have 32 bit float, there's a certain amount of numbers this float can represent, and it's not going either above that or below that. So you got to be aware of that. And then the last part, your signal got to be like framed. Like on the y-axis, we have the amplitude. On the x-axis, we have the time. If you like presented those other figures, like drawings as I did before, it's nice if you do something schematic. It's nice if you do like art or whatever. But in the end, if you want to publish your paper, if you want to get it into some decent journal, name the axis, because otherwise the reviewers are not going to know what you're going to talk about, especially in terms of what the units are and how much they're changing over all over the place. So need some framing. So since we've covered the amplifier by now, I'd said we should proceed to the yeah, how to process the signal. And here I have a couple of PSDs, which is power spectrum, which are power spectrum densities, but I'm gonna explain like a little later on. And that's basically to brief you a bit, little about what you're gonna fully understand after we finish this yeah, this subtopic. And I brought you a video here, and I hope it works. Oh yeah, it works. So what you basically saw here, I'm just jump in the middle. What you basically saw here is drawing with sinusoids, and that's basically kind of the idea behind the FFT. Instead of representing, in this case, an image, that musical note here with pixel information, like at this point you gotta have this color value, at this point you gotta have this color value. You can instead of having the spatial coordinates, you can have sinusoids representing that. And yeah, for to understand that basically a little better, we got to look into the two topics. We got to look into decomposition, because that's what the FFT does. It decomposes our signal into sinusoids, and decomposition is the first, sinusoids is going to be the second, and now we're going to look into both of them. If we have our signal here, originally we had this continuous signal, which had like an infinite number of individual states. We sampled that, we quantized that, and now we can basically turn that into a series of numbers, which would be 1, 2, 1, 0, 1, 2, 1. As simple as that. And if we wanted to split that up into, let's say, two individual subsignals, like those two here, which in sum again return the original signal. We already decomposed the signal, and that's basically all about the decomposition that there's to know at this point. Decomposing the signal just means you take one signal and you basically split it up into a selection or into a group of individual signals. And this second thing we need to look into to understand what the FFT does in a couple of seconds is sinusoids. So yeah, I got a question there too. Take a look. Bad me, I forgot to program it. Anyway, the question was, I mean, as you can read, how many parameters are really required to fully define a sine wave, and it's kind of interesting. The older the people get, the more difficult it is for them to answer the question in the end, which is probably kind of the thing we observe that although that's like 7 or 8 grade school geometry knowledge, it's just too distant over time from us, and yeah, we walk away from that over the course of our lives. But therefore, little repetition on that. Let's say we have our sinusoid here, and that's the function defining our sinusoid. We have a frequency in our sinusoid, which basically defines how often the thing loops within given a certain time frame. In this case, usually within a second. And then you have the frequency defined in hertz, which means that if you have a frequency of 20 hertz, you have basically 20 full loops within 1 second. The second characteristic of your sinusoid is going to be the amplitude, which means how small or large are those extents going to be. And the third characteristic of your sinusoid is going to be a phase, which is basically a shift in time, shifting the thing either to an earlier start or to a later start. But since the thing is repetitive, it goes to every point at one earlier or later. Yeah, and that's basically all the parameters you need to know about a sinusoid. And considering that this beautiful abomination of a super complicated formula is basically what applies the Fourier transformation to our data, it's not that difficult if you work it step by step. It just decomposes the data into sinusoids with different frequency, amplitude, and a phase. And that's basically all there is to know about the FFT. You're going to get a bunch of sinusoids with these different characteristics. And the important thing is that those sinusoids you get are going to be from an orthogonal space, which basically means they are mutually exclusive. And if we want to put that into application, we can use our FFT to estimate the power spectrum within this beautiful signal that I conjured. So we provide our FFT with some data of that signal, and then we let it run. And if we apply the FFT to that, we basically get a complex representation of sinusoids, which are basically telling us the amplitude, the frequency of the phase of the sinusoid, and then we can further transform that information to create a power spectrum density. And that power spectrum density is going to tell us how much of a specific sinusoid is within that signal. And if we take a look at the signal here, that's basically an equal distribution of those three sinusoids. And usually that's represented in this form here, which is, as I already said, a power spectrum density, usually a histogram or a line plot. Unlucky as I am, usually that's how my data actually looks like. So way more noise in my data. And when I put that into an FFT to later on get a power spectrum density estimation of that, I don't get my equal distribution of those three sinusoids. I get something that's quite different from that. And my question to you now would basically be whether you have an idea on how we can fix that. So I'm gonna provide the resolution to the enigma now. So what happens if we just increase the amount of data provided to our FFT? What we basically do is we provide the FFT with more data. And since the FFT is a perfect transformation from time domain space into frequency domain space, it cannot lose information. And since we just basically forced more data into it, it is going to provide us with more of an output. It's not going to be a higher quality output. It's just going to be more quantity. And in the case of the FFT, that more output basically means that you're going to have a finer granularity in terms of your frequency bins. If you basically have a very shallow window or provided with very little data, you're going to have super wide frequency bins, like let's say 5 Hertz wide frequency bins. And if you provide it with a really large window, you're going to make those frequency bins smaller, like 2 Hertz, 1 Hertz, half a Hertz, the more data you provide. And actually, by providing it more data this way and basically having a higher quantity output, you're kind of introducing even more noise into your data because you're running into the issue of data sparsity. And you're not going to get a smooth power spectrum density. The other answer that noise cannot be handled at this step is luckily incorrect as well. We can handle noise at this step. It's not like we have to forsake all hope yet, assuming the noise is limited to some degree, but we can handle it. And what we can basically do is we provide the FFT with more data, but we don't do it in like one chunk. We do multiple FFTs and do have multiple windows here and evaluate those windows individually. And then we average across those windows. So if we basically took two windows and we did our FFT and derived our power spectrum density from that, if we average across those, we're going to get closer to our equal distribution that we had beforehand with the not noisy signal. If we provide it with more data again, it's going to be even less noisy, and we're going to get like even higher quality results. But that's assuming that we basically did multiple FFTs and average across them, not providing them into one single chunk. So now, as I promised you, I have brought you these PSDs from a couple of papers, and basically in this PSD, you're seeing that you can see there's a high frequency peak at the 7-8 hertz mark, and let's say at 17 hertz. And that means like whatever signal was investigated there had can be represented to a large percentage by a sinusoid, which has a oscillation rate of that 7 hertz or that 17 hertz, but kind of encompassing a large quantity of the signal observed there. And the same applies here. If we take a look here, we see that the frequency peaks at 25 hertz. And if we basically, that basically allows us to make the conclusion that at, let's say, 20 to 30 hertz, we have, if we take the sinusoids within that frequency range, they represent a significant chunk of the power that we just observed. Doing an FFT is tricky, and doing it correctly even a little bit more. So I also want to provide a coding sample for that. And there are a lot of parameters, and actually it looks kind of fiendish, but there's not so much that you can actually do wrong with that one. Let's say you're provided with your data, which is going to be a first parameter. Then you have to provide it with a sampling frequency, of course. If you don't provide it with a sampling frequency, it's going to basically estimate that the highest frequency in your signal is going to be exactly 1, and every other frequency is going to be a fraction of that. So it's just for scaling your x-axis. Then you apply a window for smoothing your data, which usually you can just go with the default one. There's like very rare edge cases that just doesn't apply. It's rare. And then the other two more important factors are going to be the length of your data segments. The longer your data segments, the more fine granularity is your power spectrum density in the end again, which means you're going to have smaller frequency bins. If you provide it with short data segments, you're going to have large frequency bins. And then, of course, since this is this particular example, I chose a Sparse method. It doesn't do concatenating data chunks out of your the data you provided it for the averaging later on. It even overlaps them to basically adequately represent whatever is happening at the junction between two of your data chunks. And that's basically all the parameters you would have to set. All of those other parameters are quite situational and rarely ever have to be adjusted. So to give you an example of that, if I wanted to do a PSD on some data I just acquired. I'm going to put my data in there. I'm going to define the sampling frequency as, let's say, 5,000 Hertz. Going to go with the hand window, which is in Sketch just the default window. And if I now set the sampling number per segments to 5,000, I would end up with 1 Hertz frequency bands. If I set it to 2,500, I'm providing it with less data in each segment. So I'm going to get wider frequency bands. If I'm going to provide it with 10,000 data points, I'm providing it with more data. Therefore, it needs to represent more information. So the frequency bins become smaller. Yeah. And since you want to average across that, if you basically select here a high number, and considering the data is more sparse, you're going to need substantially more data if you want to increase the frequency resolution much lower than 1 Hertz usually. Whereas decreasing the frequency resolution to 2 Hertz, 4 Hertz, or 5 Hertz, or something like that can, if applicable, significantly reduce the amount of data you need to get a solid estimation out of your PSD, of your FFT for PSD. And then in the end, a couple of different methods for applying that power spectrum density. Of course, I just explained how to do that with an FFT. Theoretically, you could also do a wavelet decomposition, which decomposes the signal into individual wavelets and basically produces something similar. Or you could go with a multi-taper approach, which is also FFT based, but the difference would be that this applies multiple FFTs with different filter windows, and all of them have like slightly different reasons for being. And this is going to be the last topic for today's session. I'm running short on time. When you apply frequency filtering to put the FFT stuff into a little more, to give it a little more like application examples, you can either go with an infinite impulse response filter, or you can go with an FIR filter. And the original filter for getting rid of a specific frequency is the IRR filter. And the thing is old. That basically dates back to when people had to sit in the labs with and soldering little electronic pieces into the circuits, and that's kind of where the IRR filter comes from. It's usually an analog filter. Since people used to have to solder that onto their boards, it's limited in the number of components, and making that a short, like small component filter means it needs little signal and thereby is short, is fast. On the other hand, if it's only provided with little data, the suppression that the IIR filter provides is not as strong. And another disadvantage is if you want to like extend them to basically get super strong suppression factors, you're going to run into the issue that your IIR filter is going to get unstable and has basically all kind of weird hiccups that you're going to need at least a bachelor's in digital in signal processing for, something like that, to fully get rid of. So the simple answer is, if you do like stuff on a PC, go with an FIR filter. FIR filters basically you most times use way more data than IR filters, but they provide a significantly stronger suppression of artifacts. And while that may not seem as much of an issue if you look at the difference in amplitude across your EEG signals or EMG signals or MAC or whatever, you're going to have a significantly high amplitude line noise and a even more significantly high amplitude deep brain stimulation noise. They are going to be all over the place amplitude wise. So you need a strong suppression, especially if you want to record data from that is somewhere in the vicinity of those noise sources. So yeah, I think that's the last question for the day. Basically, since I already introduced you a little to that, under which circumstances would you use an FIR filter, and when would you use an IIR filter? Okay. Looks good. As I said, you should ideally use your FIR filter for offline stuff, digital filtering, anything where time is not as much of an essence. And yeah, your IIR filter is the ideal solution if you want to do something analog, because you don't want to be sitting there and gluing or soldering 10,000 of elements onto your circuit or something like. And the other application that basically I could come up with would, if you were to apply some let's say something really time sensitive, like adaptive, if you did some adaptive DBS algorithm that would have to react within the millisecond time scope, you would have to do something like the IIR filtering, because there's just no way you could get your FIR filter to respond within that time frame. Just would be out of the question. Since I basically now talked so much about that filtering stuff and didn't provide a single example, that's going to be now. Let's say we recorded a signal, and what we recorded looks like the upper signal, but what we actually wanted to have looks like the lower signal. And if we look at the amplitude, that's like scaled from 20 to -20, whereas the lower signal is scaled from 2 to -2. So we're going to have, with the upper one, we appear to have a significant kind contribute at a certain frequency that totally dominates our signal, makes it almost impossible to see anything in there. So if we transform that via our FFT into power spectrum density, we can basically see that the upper signal has this super high peak here, right at 27 Hertz, whereas the signal that they actually wanted to have looks like that. And this is just an example. It doesn't have to be 27 Hertz. It could be whatever kind of artifact you picked up during your recording. Could be the line noise, could be the DBS artifact, whatever. And if we want to get rid of that now, we can apply our filter, either FIR or IIR, and then we would basically get something like this here from the upper one. And as you can see, it's not a perfect match. There is some hiccup here, and this hiccup is right at the frequency where we applied this filter. And this is because if we apply our filter, we can, for example, apply it as a band stop filter, which notches out a certain frequency. And if we do that, we basically invalidate any information that's within this frequency area here. It gets toned down by a significant amplitude, but doesn't get like totally zeroed out. There's going to be some residual. And the more data you feed into it, the stronger the suppression factor usually. So if you feed like little data into it, like I did here on purpose, you're not going to even tone it down to 0. You're going to have some residual activity here. But that's not the original signal. That's just insufficient suppression. So anything in between where that artifact was, it's basically now invalid for further evaluation. And if you want to like evaluate that, you're going to have to make sure that the suppression you applied is sufficient enough to basically botch that down to almost 0. Then you can basically ignore it further on. But you got to plot it, and you got to make sure that that's actually the case. If we transform our signals back into time domain space, we are not having these. We're not going to have this like artifact dominated signal anymore. Now we have this red filtered signal here. And as you can see, it's not a perfect reconstruction of the signal that they actually wanted to have, but usually it's sufficiently close, and the error is within the not meaningful range. And yeah, some coding again. So if you want to do that on your data now, and let's say you want to apply, in this case, I brought you the example of a band pass filter, which is kind of the opposite of what we just saw. The band pass filter allows you to define a low frequency and a high frequency, and everything within this frequency range is basically going to survive the filtering, and everything outside is going to be almost zeroed out. So what you're gonna supply this, what you're gonna have to supply this one is basically data, then the frequency range you're gonna apply, and then we have this other super important factor here, which is gonna be the transition width. And the transition width determines how steep your filter is gonna be. And you want it to be as steep as possible, but on the other hand, making the thing steeper requires more data. Yeah. And then the other factors are more like, how strong do you want your suppression to be? What's the sampling frequency? That's more, it can usually stay with the default. And some applications example would again be, let's say you want to filter your signals into theta, alpha, beta, or gamma. You're going to have to filter them into brackets of 4 to, you can filter that into 4 to 7, 8 to 12, 20 to 30, or 32 to, for example, this one I selected none here, and if I select none, it becomes a high pass filter, which means everything above 32 is going to stay valid. Everything below 32 is going to be notched out. If you filter your data and you're going to get a reviewer that's going to tell you alpha is, let's say, 7 to 12, and you applied your filtering incorrect, and you basically have no idea of what you're doing, you can be like almost 100% certain that reviewer has no idea what he's talking about, like none. If you apply that filtering, if you have like slightly overlapping filter windows, or you have stuff like that, or you have like close by windows, they have like tiny gaps, that usually doesn't matter. The frequency spectrum you're looking at with electrophysiological signals is usually smooth, which means if you cut off like a tiny bit of it, that should not have a significant impact on your results. If it does, there's usually something wrong with the analysis in the first place, but yeah. So having dived deep into what the FFT does, what the PSD does, and all that sampling stuff, I promised you to basically take a look again at that sampling signal that we looked at early on, and what happens if we undersample our signal. And I wanted to basically take a look at that from the frequency domain. Let's say we have this signal here, and we want to sample it. So we have our peak here at 20 Hertz. So we can say 20 Hertz times 2 is 40. I'm going to sample it at 40 Hertz. And we're going to end up this non-beauty here, which basically means we just cut into our 20 Hertz bin, which doesn't have a proper amplitude anymore. And our artifact here at 130 Hertz got wrapped around and around and around within this 20 Hertz block, which basically subtracts 20 Hertz from this 130 Hertz peak as many times until it stays within that bracket of 0 to 20, which 130 minus 120 puts it at 10 Hertz. And then having these two components here, they're going to get summed up. So you're going to end up with the upper one, which means you're going to have like a super high peak at 10 Hertz, and the 20 Hertz peak is dead, for lack of a better term. So let's sample it at 100 Hertz, because we're going to have a 20 Hertz peak, and we are interested in 20 Hertz. So 100 Hertz is certainly higher than 20 Hertz, even higher than 80 Hertz. And that's going to introduce the same issue all over again, partially. We managed now to properly sample our 20 Hertz peak, but we are going to still having that issue that we didn't properly sample our 130 Hertz dBs artifact. The thing now sits at 30 Hertz. And if the thing sits at 30 Hertz, it's significantly going to impact our analysis of, in this case, whatever happens at beta and gamma frequency. And then we can, the other option would be to sample at 270 Hertz, for example. Then they're going to get a proper representation of our signal, because the high frequency we had was 130. 130 times 2 would be 260, and with 270, we are well beyond that. So that's kind of the first session of this workshop, and I almost managed to stay in time, and I think we should do some Q&A now.